Okay, this is the last chapter, chapter 13, the longest chapter, and there are quite a lot of topics that we need to cover. Okay, model specification criteria. Okay, the third slide quite self-explanatory, and then it's about the criteria for a good model, good econometric model, and then I think I explain each bullet in nice detail in the study guide. So please refer to the study guide. Okay, so I'm not going to repeat the same explanation in this summary video. Okay, and then for this chapter, we focus on these three types of specification error. What if you use the wrong functional form? What if you commit overfitting, meaning you include an irrelevant explanatory variable? And then underfitting means what if you exclude a relevant explanatory variable? So I'm going to start with the easiest one, using the wrong functional form. Okay, this is just a hypothetical example. Let's say the correct model should be linear function y as a function of x, but somehow you made the wrong decision. You run the regression incorrectly as a reciprocal model y as a function of 1 over x. And then there will be two consequences. First one, your slope parameters would most likely have the wrong sign, contradicting theoretical thinking. Second consequence, you will have some weird patterns of the residuals. In fact, they may no longer be normally and randomly distributed anymore. Okay, so these are the two consequences, and they are both bad consequences. Okay, and then the remedy is easy. Just make sure you use the right functional form. I think the graphical sketch XY scatter plot would give you a good hint as a start to determine what type of functional form you have to use. Should you run it as a linear model, double log, log lean log, and so forth. Okay, and then I want to move on to the next one. Okay, what if you commit overfitting? You include an irrelevant explanatory variable. Okay, so this is the example. This is the correct model, y as a function of x2, and then the wrong model, you somehow include an irrelevant explanatory variable, x3. So I repeat, x2 is relevant, but x3 is irrelevant. So in this second regression, you commit overfitting. Okay? And then the remedy is easy. You have to drop an independent variable as long as the theory proves that this variable, let's say x3, is irrelevant. Then what is the point of including it? Remember some funny examples in the past that we include size of the bathtub, size of the garden, the number of dogs as explanatory variable to explain your marks. It doesn't make sense at all. And then these are the consequences of committing overfitting. Your R square would increase. Remember the weird characteristics of R square. As long as you add more explanatory variables, even if they are irrelevant, R square would definitely increase. But if you commit overfitting, although R square would increase, your adjusted R square would decrease. Second consequence is fine. Luckily, if you commit overfitting, not much of an influence on your parameters. They remain unbiased and consistent. So the parameters are still fine, actually. And then the variance of the error term is still fine. It is still correctly estimated. But now, by committing overfitting, the standard error of the parameter would definitely become larger. Okay. And then since the standard error of parameter becomes larger, then it would have some impact on the reliability of confidence interval and hypothesis testing. Okay, so for example, if the standard error of the parameter becomes larger, then the confidence interval will be wider, actually. Okay, and then I have an example in the in-class exercises, okay, with some numerical examples. So we can look at these two regressions. The first one is fine, but then the second one I commit. Or first one, marks explained by study hours, party hours. It looks fine. Second regression, marks explained by study hours, party hours, and the number of times you clean your bedroom. So x4 is irrelevant. Okay, so we commit overfitting. And then for this first regression, I use B1, B2, B3 head, and then the second regression, I don't want to use beta anymore, otherwise it would confuse you. I rather use C1 head, C2 head, and so forth. Okay, so let's look at the consequences. Constant and slope parameters remain fine, unbiased, and consistent. In other words, on average, these sample regression parameters, the expected value, will be equal to the true value. And you can't just name the consequence, you need to provide additional information, refer back to the given information. So we have to compare one parameter at a time. Do you notice by committing overfitting, there isn't much of a change to the constant parameter, still hovering around 79? The slope parameter in connection with study hour also not much of an impact by committing overfitting. It's still around 1.95, 1.96. The next slope parameter in connection with party hours, not much of a change. Even if you come after you commit overfitting, it's still around minus 2.46. Variance of error term remains fine, correct? Do you notice not much of a change? Around 135. But standard error of the parameter becomes larger. Do you see standard error of the constant becomes larger? From 3.47 to 3.8 something. And then again, standard error of B2 head increases. You definitely see the upward bias. And then for the next one as well, upward bias. And then the last one is the easiest one. R square increases, but adjusted R square decreases. Okay, happy with that? Okay, then underfitting. Okay, this is the correct model. Y as a function of x2 and x3, and both of them are relevant. But then you inexplicably decided to drop x3 when you rerun the regression. So you run the wrong model, y as a function of x2. You omit the relevant explanatory variable x3. So the remedy would be, please add back the relevant explanatory variable. And then let's look at the consequences. Actually, the consequences are much more worse, more serious when it comes to underfitting compared with overfitting. First consequence, by committing underfitting, both R square and adjusted R square decreases. Okay, I want to skip to the fourth one. This time, the variance of error terms is incorrectly estimated when it comes to underfitting. Remember, for overfitting, it is still fine, correctly estimated, but not anymore when it comes to underfitting. And then standard error of the parameter is biased, but we don't know the direction of the bias. Remember, for overfitting, we know it is upward bias, but for underfitting, we don't know the direction of the bias. But as long as the standard error of the parameter is biased, then it would have impact on confidence interval hypothesis testing, because they will become unreliable, giving you misleading conclusion. Okay, now I want to go back to the second and the third bullet point. Okay, now we already know x3 is a relevant explanatory variable, and we exclude it, then we commit underfitting in the wrong model. But now I want to know whether x2 and x3 are strongly correlated, because the answer of this question would have an impact on these constant and slope parameters. So let's look at this case, the worst case. If x3, the omitted variable, is correlated with the included variable x2, then sorry, both the constant and slope parameter are biased and inconsistent. Then it means game over. So it means both alpha 1 and alpha 2 in the wrong model are biased if x2 and x3 are correlated. Then the slightly better case, if the two variables, x2, the one you still include, and x3, the omitted one, if x2 and x3 are not that strongly correlated, your constant is still biased, but luckily this slope parameter in connection with x2 is still okay. It is now unbiased. And then later I'm going to look at this, not now. Okay, I will come back to this later. In case x2 and x3 are really correlated, and then I omit x3, then what is the impact on the direction of bias on this slope parameter? And it is determined by this equation, and I will refer back to this later, not now. So I want to go to this. Okay, an example. Again, the detailed explanation can be found on the study guide and in-class exercises. So let's look at the first case of underfitting when x2 and x3 are not that strongly correlated. So let's look at the first regression. Marks explained by x2 study hours and x3 parents' education. Yeah, indeed, there are really some studies in economics of education that found out that parents' education really have an impact on the kids or the children's academic performance. And then I commit underfitting in the second regression. I only include x2 study hours, but I omit x3 parents' education. So now we have to think, what is the correlation between x2 Study out the one we still include and the omitted relevant explanatory variable, X3 parents' education. My argument is that X2 and X3 are not that strongly correlated because I've never heard of any studies proving that if the parents are strongly educated, then the kids will study harder. Okay, maybe a little bit of correlation, but not particularly strong. So, for instance, my father never went to school because of poverty, but somehow I actually was okay as a student. I studied long hours. So, meaning there isn't really a strong relationship or correlation between X2 and X3. Then we have to explain the consequences. Since X2 and X3 are not strongly correlated, then only the slope parameter become biased, but the only the constant parameter is biased. Do you see the huge change now? From 60 to 40. But then the slope parameter in connection with X2 remains unbiased because X2 and X3 are not strongly correlated. Do you see not much of a change there? Around 0.91, 0.92. And again, if I ask this type of question, you can't just name the consequence. You have to provide additional explanation by referring back to the given statistical information in the two regressions. So for the official answers, please look at the study guide and the in-class exercises. But since this is underfitting, the variance of error term is no longer correct as a result of underfitting. Do you see the huge change here? From 400 something to 800 something. Standard error of the parameter becomes unreliable. Do you see the standard error of the constant? There is an upward bias. And then the standard error of B2 head, it drops. Remember, for underfitting, we don't know the direction of the bias on the standard error of the parameter. It could be an upward bias, as in this case, or it could be a downward bias, as in this case. Last one, the easiest one, R squared decreases, and adjusted R squared also decreases. So this is the first case of underfitting when X2 and X3 are not that strongly correlated. Then the next case, this time, the second case, when X2 and X3 are strongly correlated. Okay, marks explained by study hours X2 and party hours X3. And then in the second regression, I commit underfitting because I omit X3. I think we all know X2 and X3 are quite strongly correlated because those who spend longer time studying, they will spend less time partying. So this time, since X2 and X3 are correlated, then by committing underfitting, then it causes both the constant and slope parameters to become biased. Do you see the huge change in both parameters? Okay. Standard error of the parameter, unreliable. Do you see it goes up for the first one and then it goes down for the second one? Okay. Variance of error term is no longer correctly estimated. Do you see the huge change between the two regressions? The last one is the easiest one. Both R squared and adjusted R squared decrease. Okay. And then to conclude, there is a nice summary table question here. Okay, very self-explanatory. So I'm going to stop for 30 seconds for you to go through the answers. So this is the most serious case, underfitting. When X2 and X3 are highly correlated, it is going to ruin both the constant and slope parameter. Okay, so we are done with the first part. Okay, when we return, I will refer back to this part about the impact of underfitting on the direction of the bias on the slope parameter of X2, the variable you still include. But what if X2, the included variable, and X3, the omitted variable, are strongly correlated? I want to find out the impact of excluding X3 on the slope parameter of X2. So we are going to look at 3 questions in the next video.